about that. I was muted. I was actually trying to prepare some slides, and unfortunately, I ran out of time. We will cover definitely what I've prepared so far, which is what you see on the screen right now. But it has animation, so we'll give you a gentle introduction to all these lines here. And
that's a lot of lines.
Yes, that's the reason why my previous diagrams didn't have all the lines. But I realized that it's important to cover them all. But if we go them one by one, then it's not really that painful. I thought today I should do a recap of the entire V3 up to the point that we have described. So I'll do that using this diagram. And then after this, what we can do is we can brainstorm a little bit about what it would take to implement the union opcode. And then if time permits, we could go into the code, or we could postpone that part completely to next week. So here it goes. All right, so this is the same example that we saw yesterday, but we are going to take a more holistic approach of the example and actually look with a microscope about what happens for each step. So initially, the parser, the analyzer, the parser has done, it has built the AST, and the analyzer has just got the SQL and is beginning to analyze it. So the first thing we analyze is the from clause. And the from clause, we go look at symbol A, and we say, okay, now let's build a route for A, which is R0. And because there is no where clause or any other constraint on it, it's a full scatter. So this part is obvious and straightforward. We've already covered this. But as soon as we build this, we also have to build the symbol table for this select query or this route, as it were. So what are the relationships between the symbol table and this data structure? So here, as you can see, I have used 3 colors, and actually 4 colors eventually. Each color denotes a realm or a world. The green color denotes the opcode world, which is basically anything that's a route, a join, or basically things that VTGate has to perform as action. The white or gray symbols basically denote the AST world. Those are things that will eventually become a query at the end once we have finished building the plan, which is basically the AST world. And we have the red color, which is the symbol table world, where we have data structures that tells you where things are and what things are and where they are. So in this respect, the darker red is actually a symbol table, and the lighter red is actually a symbol inside the symbol table. So yesterday I mentioned that a symbol table is built for each select, but that is actually an eventual truth, not an immediate truth. So in this particular case, for example, I have a symbol table, and it only contains A as the table name. And it will eventually be for the select that we are analyzing, but right now it's only for this table. And in terms of relationship, the symbol A that I created based on the fact that I saw the table name A here. And I've also said that this symbol A belongs to route 0. This should be fairly obvious. The other thing that I've also done is that I've said that route 0's symbol table is the big red square. So route 0 points to the outer symbol table. And to understand these relationships, we can ask ourselves, why do we need these relationships, right? The relationship that a route points to at the symbol table is somewhat of a convenience because I do pass this route around for analysis. And whenever I pass, I go and look at things inside the route. And sometimes I find a new symbol, and then I want to see where it is. So I need to send that find function to a symbol table. And basically, the route tells you which symbol table to use to search for symbols. So that's the reason why we have the relationship that goes from the route to the symbol table. And a route is guaranteed to point to only one symbol table, which is the select statement for which the route belongs. And the relationship from a table name to the route exists for the most important question, which is where is this table being scanned? Which transitively applies to any columns that reference this table. So if there's a column that references, if you have a.c, then we know that, is it a.c? Yeah, a.c. Then a.c is produced from route 0. So any questions so far? This is the stuff that we covered 2 days ago, and this should be fairly straightforward, unless you have any questions. So now the next thing that happens is we continue our journey and end up at node B. So we need to build the same thing for node B. And when we build node B, as I mentioned, the recursive algorithm works in such a way that it is unaware of the other part of the join. And therefore, node B has a very similar data structure as node A. They are they look very similar. So it has its own symbol table, except the table name inside there is B. One question you may ask is, why is there no line going from this table A to this symbol A? And the answer to that question is, yes, even though that relationship is true and it exists, that relationship has no use for us. I mean, we could say that, yes, A, put a hard pointer from A to this symbol A, but we actually don't ever have to use that relationship, and therefore we don't store it. That's the simple answer. But otherwise, yes, the A that's inside this route and the A that's in the symbol table must ideally have a relationship. Make sense? All right, so now we have done this. Let's see if there's any other questions we have to ask ourselves before proceeding. So what are the relationships? We have now introduced 3 relationships. We have introduced the relationship from a route to an AST. A route contains an AST. And we have introduced the fact that a symbol points to a route. A symbol always points to a route. I mentioned before that symbol, as this engine evolves, a symbol may end up pointing to something other than a route. But for now, it is true that routes are the only ones that can produce a symbol. And we have introduced the relationship that every route points to the symbol table that is being built with it. The early implementation of V3, this pointer did not exist. And without this pointer, the way the code was is I was actually always passing a route and the associated symbol table through the entire call stack. And I realized that there's no point in doing that. So I just pushed, in some respect, made the route point to the symbol table, which means that I only hold on to, so my main starting point is always the route. And then if I start with the route, I can always reach all parts of my data structure. So that's basically why this arrow exists. So now we are going to continue, and then we are going to encounter the join. So when this join happens, a bunch of events take place. The first thing we do is we create the join opcode and make it point to route 0 and route 1. Route 0, they are still route 0, which means that the first thing we have to do is rename route 0 to route 1, which you will see in the animation. Unfortunately, the sequence is incorrect. So and then what we have to do is, because the join is bringing these 2 routes together, the two symbol tables have to merge. So then this is what happens. That other symbol table is thrown away. We rename route 0 to route 1 for table B. And we add B here to the previous symbol table, the left-hand side one. We could also build a new one if we liked. It doesn't matter. And then what we do is we say B points to R1.
So you actually throw away the other symbol table.
Correct.
Okay, you don't try to merge or anything.
It is a merge of the other symbol table into this one. That's how we could look at it.
Okay, so you actually take the content of this symbol table. The other one. Okay, you're not like saying, oh well, now that it's a join, let's like refine the symbols, and now we're just adding them into this symbol table instead of the other one. You're not re-adding symbols. You're actually
yes.
Okay. So it is actually a merge. Yeah,
it is a merge. Yes. Unfortunately, my animation skills are not that great enough where I could show B traveling from there to here.
That's actually desirable, because I would much rather you be a good database writer than an animator. If you were too good an animator, you should get some job doing something else. We'd much rather have you do Vitess.
Sounds good. Let me make a note of that. All right, so now we see that B, that's the reason why B continues to point to R1. So we renamed R0 to R1, but B continues to point to the old route that it was pointing to. So we actually moved B into the symbol table. And obviously, R1 has to be pointed to the new symbol table because we threw away the old one. And so now, so with this data structure, my starting point is always the current opcode that I'm working on. Like, in other words, if I have R0 or R1, everything is reachable. And in this particular case, it will be actually the join node that I will hold on to. I believe there is a pointer from the join node to the symbol table. I will have to go look at it. But if there isn't one, there is actually a logical reasoning why that pointer should exist. I may or may not have actually implemented it, depending on whether I actually need to use that relationship. But if there was a need to use that relationship, we should not hesitate to add that pointer in there. So that is, so legitimate relationships are from the opcodes to their symbol table. And the symbol tables contain symbols, and symbols point to the opcodes that generate them. At this point, the only opcode that generates symbols is a route, and therefore those symbols always point to a route. And a symbol also knows which symbol table it is part of. It's a relationship that we'll use later. I have not represented it here yet. I basically didn't have the time. So there should actually be an arrow from A into the outer table and from B to the outer table. All right. Anything else that needs to be covered? Nothing. So here the thing that was not clear when I was thinking about it, which is pretty obvious now that we look at it, is there is one symbol table per select. And there can be multiple routes or opcodes per symbol table. So you cannot have a pointer from a symbol table to the symbol table itself into anything, because a symbol table kind of represents multiple opcodes. But a particular symbol has to have has to belong to a route. Okay, let's move on. What happens next? What happens next is we push A.n equal to B.n into the rightmost route. And how did we do that? Is we scanned A.n and B.n, found that the rightmost route is R1, and that's why we pushed it there. So now let's see what happens to the relationships. So A dot n points to A, and B dot n points to B. This is when this is a new relationship, which means that any column reference inside the AST has a pointer to an actual symbol. And the reason why we need that relationship is because then we can ask ourselves the question, are you local? So if you ask A.n, are you local? It'll say, oh, let me go check symbol table A. A goes to R0. No, I'm not local because I'm currently analyzing R1. But if you ask that question from B, obviously it'll go to B and bounce back into R1. And then we can say, yes, we are local. So that's the most important question that we have to answer. What else? The other question that you can answer with this relationship is there a Vindex on this particular column? Because if there is a Vindex, then the symbol table will tell me that, which actually I didn't represent here. But for example, B would say that n is a Vindex for B. And therefore, when you ask whether B dot n is a Vindex, it'll say, yes, B dot n is a Vindex. Therefore, you can improve this route to an equal route instead of being a scattered route. Cool. So we have route to AST relationship. We have symbol to route relationship. We have route to symbol table relationship. And now we have just introduced column identifier to symbol relationship. It's getting complicated, but it's still understandable from just the use cases, what we use these relationships for. And now we encounter the subquery. So the subquery, I fast forward all the way to the end of the subquery analysis because it is basically the same process that we would have done for the original query. So the subquery is now fully built, where I didn't obviously draw all the lines, but there are some lines that are there to show as example, like c.id points to C. There is this symbol inside the route points to, inside the symbol table points to its route. The route points to the symbol table. And this symbol table itself has a parent, which is the outer symbol table.
Okay, Sugu, so, and you're just using yellow here for the fact that it's a subquery.
Yes, so it is actually green.
This thing is like green, the white is still, yeah.
But so this is a green symbol, which has been yellowed out because it's a subquery.
Sure.
And also, call is a call sim, and A, B, and C are table sims, right?
Correct. That's why call is on top of C. It kind of hides what's underneath.
Yeah.
So when you search inside the symbol table, you'll first match call, and if there is first match things at the call level. If nothing matches there, then you go to the table symbols and search there. So I think up to this point, I had you all with me yesterday, right? It's only after this point that hell broke loose, if I remember right. So now we look at this symbol table. We analyze this. And so there is one more thing that actually, which is going to happen on the next level, is that while I was building this, I encountered b.id, right? So b.id is actually a reference to the outer symbol table. So what should happen here is that we need a line that goes from b.id all the way to b. Because what happens when you search b.id inside this symbol table is it'll search inside here, not find anything, and say, OK, outsource to parent, and then it will search there and find b. So b.id will point to this b, which you'll see in the next animation. But one more thing has to happen. This symbol table, like I mentioned yesterday, should record that b or b.id was an external reference. So that's what happens here. Line goes from b.id to b, and we record b as an external reference. So b is kind of coated yellow also. I guess I should use a different color, which stands for external symbol. So what is this external symbol used for? So let's say we have finished analyzing this subquery. The subquery function analysis has returned, and this is the exact data structure that we have at this point. And now what we have to figure out is, what do we do with this subquery? And once a subquery has finished analyzing, it's practically just an expression. It is no different than this a.n equal to b.n, or this a.id equal to 5, right? And so what do we do is, what do we do with a normal expression? We apply, we try to apply the rightmost reference rule. So what we have to do is, we have to say, okay, inside this expression tree, what are the symbols that reference elements of the outer query, right? What basically, who is anyone that's referencing A? Is there anyone that's referencing B? So that question we answer by looking at the external references of this symbol table. So basically what I do is, okay, the subquery has returned symbol table, give me all your external references. And then using those external references, I apply the rightmost subquery rule to identify the target route, the potential target route for this subquery. So obviously, the answer to that question is R1 is the potential target route for the subquery, because this subquery references B somewhere inside there. Make sense so far? Oh, the other thing I actually did not add. Is there a question? No question. Okay.
Nope. I was just going to say all clear.
All clear. Okay. So the other thing I forgot to add is, what is the route for this subquery? I should have added a box in here that says that this is actually a user, and it's an equal route, and the route value is b.id. Right. So this is actually a route that actually uses b.id. So then, so the one thing I do is I identify the target route. Then I ask the question, is the subquery's route the same as my target route? And if you look in the code, actually, it is called isSameRoute. That's the name of the function. So what that thing does is, it looks at the R1's route and compares it with the subquery's route. And if the routes are mergeable, in this case they are, because there is a b.id constraint on this route, and therefore they are mergeable, it will say, yes, they are the same route. You can merge this subquery into R1. So let's go through the motions of merging. So what we do is, we push that AST item, a.call in the subquery in here. And
sorry, Sugu.
Yeah.
So mergeable, the conditions for mergeability,
yeah.
I mean, if they're the same route, then sure. Well, maybe we talked about this on a different day. What else is there to mergeability? I mean, do we only merge when it's the same exact route?
Yes. The same exact route is not the correct way to describe it. It has to be either the same exact route, which would be both target the same unsharded key space, right? In that case, it's the same exact route. The other condition is they both have the same Vintex constraint. Basically, if R1 had b.id equal to 5, and the subquery also had a b.id equal to 5, right? Then they are obviously mergeable.
Yeah.
Or the third condition, which is actually the more common one, is that it's a correlated subquery, but the dependence, the correlation is dependent on the same primary Vintex as the outer route. So basically, if R1 had a route that was controlled by b.id, and if the subquery was constrained by a b.id equality, then those routes are mergeable. Because a dependent subquery which is using the primary Vintex of the outer query, its rows are always present within the same shard. I think we went through this in our second session. For in the case
I
of
think you're right. I'm remembering now. Thank you.
Yeah, in the case of a join, so the same rules that apply for a join apply here also. And the best way to the best way to reason about this is to use an example. Like if you used, let's say, select star from order, and let's say items of an order are always co-located with the outer order. Let's say B is the order table and ID is the order ID. And let's say items are items that belong to an order. And let's say items also have C.ID, which is the same as, which is the foreign key to the order ID. Then all the item rows will live with their corresponding order rows. So if you used a subquery to actually drive if the outer query used order and the subquery used selected on items, then you are guaranteed that those rows will be in the same chart. So that's so it's actually much easier to reason about this if you took some use cases. And then you can generalize, and then you can go for mathematical proofs, which I didn't go that far. All right, so now we are in bad shape, though. The reason why we are in bad shape is because we have pushed the AST down. So which means that if you walk this AST, you go select B, and then you go here, and then you are inside this select, and you go inside here. And now let's say we are doing the wire up, right? We are going to see what are the external references. We are trying to see any external references in R1 that needs to be pulled out of R0, right? So if you go inside here and then ask the question, okay, C.ID, are you in the current, like, are you local or are you coming from the outside, right? If you ask that question to C.ID, it'll go here. It'll say, oh, C, and C points to R0. You say, I belong to this R0. And then I look at R0, oh, that is not the same as R1, therefore C.ID is foreign, which is actually the incorrect answer, right? What should have been the correct answer is, oh, this subquery was merged into the outer query, which means that all the symbols that are inside this symbol table actually should be pointing to R1. Right?
Yep.
And only B.ID should say that it is outside, because B.ID is coming from R0. So how do we solve this problem? So basically this data structure is messed up, and so we need to fix it up. There are a few ways to fix it up. One is to go actually chase down all the symbols inside here and repoint them to R1. That sounds like a good idea until you ask the question, what if this subquery itself had a subquery and there was a symbol table inside that subquery? How would you go chase down that subquery and fix all its symbol tables, all the symbols inside that symbol table to point to R1, right? So this is not a problem that is restricted to the current scope. The fix-up has to happen to all subqueries scopes. So that's a problem, right? So in order to resolve that problem, instead of going and chasing down all the symbols inside the symbol table and fixing them up into R1, there is actually another. Is there another complication? Actually, there is no other complication. This is the only one, because a symbol table has its full list of symbols. We could solve this problem another way, right? If every parent symbol table knew all its children, then yes, we can actually use that relationship to chase down, right? If this symbol table knew all its children, then you fix up the symbols here and then go to its children and fix up the symbols there, and you can recursively go all the way. But then it's unnecessary data structure, because now instead of a child remembering its parent, a parent has to know all its children. Instead, what we do is, there is a much simpler way to solve the problem. is to basically add a redirection at this route level, saying that this route is defunct. This route does not exist because it has been merged with its outer route. So we remove anything. We basically remove all pointers from this route and say that this route points to R1. So now if you ask the question, where is C.ID? It will go to C, C will go to R0, and R0 says, oh, go to R1. And this will work recursively also, even if there were subqueries, because if there was a subquery before, when that subquery merged into this current outer query, it would have pointed its route to this route. And this route would now point to R1, which means that if you merged multiple subqueries all the way up, they will all point to the ultimate root route. So this problem is agnostic of subquery nesting levels. Sounds good?
That all sounds good. One thing you had mentioned was that B.ID was referring to R0 a while back. Wouldn't it refer to R1 since it goes to the root symbol table and B points to R1?
Oh, you're right. Yeah, it refers to R1. Cool. You're correct. And B.ID will not be renamed to a bind variable.
Yeah, exactly.
Yeah. But if there was an A.N in here or an A.ID, that would actually resolve to R0 and would have to be changed to a bind variable.
Right. The only other question I had was, I'm not sure, I can't remember if this was covered in a previous session, but all of the route types, I can't remember, the squares have been like user scatter, user equal. What is user, and are there other types?
Oh, I should have called it order. So this example was for the user key space. That's what it stands for. It's
okay.
Yeah.
Okay.
I should have called it order key space. I think initially when I presented this, I was using users and items, or users and videos, or users and music.
Gotcha.
Yeah.
This is what the tests are written for in Vitess. So I figured that might be it, but.
Yes, that's the one. So user and music is what it is. All right. So I think this is the last of, this concludes all the lines. So I hope this has brought clarity to what I was trying to explain yesterday as to why these arrows exist. So let's actually go and look at the model again. This may actually become more clear now. So in that example, we looked at the primitive redirecting to itself, which is when a subquery merges to the outer query. The join has a left and right relationship, so it points to itself. A route contains an AST, so that's straightforward. An AST points to itself because it has nodes. A node, a column identity node, points to a symbol. A symbol points to its route. A primitive points to the current symbol table, which corresponds to the current select statement. So all these we covered in the example. This we did not cover is a call sim points to a tab sim if there is an exact underlying representation for it. So if you selected a simple column select, if you performed a simple column select, then we know that that is the case, and we actually point to the underlying table.
You mean simple, just like A.ID, rather than like A.ID plus 5 or something?
Correct. So if it was A.ID plus 5, then it has no underlying representation. And the last one, which I did not cover, which is actually the contained in relationship, which actually is something that can now be very easily explained. So in here, after we finished analyzing the subquery, we were iterating through all the external references of this symbol table to figure out the rightmost route, right? But what if this query that we are analyzing is itself a subquery? And what if the external symbols listed by this symbol table referenced some of them referenced to symbols in here, and some of them referenced symbols that were outside the subquery? We need a way to know. So when we find the rightmost route, we have to actually ignore symbol references that were outside the current level of my select. And that is where we use this contained in pointer. So basically, when we perform the search, it will say, yes, the symbol has been found. And then I can ask, well, was the symbol part of the current symbol table, or was it outside? Right? Because if it is outside, then I'm not going to take that into account to figure out what the rightmost route is. So that is the reason why every symbol has to know which symbol table it's part of. Cool. So I think I have explained all relationships and all their use cases. I think this is, you'll probably have to go through a few more exercises to become comfortable with these data structures, but at least I think there is enough information for you to be able to start understanding things. And you can always go back to these rules. When you make a change, if you are doubtful about whether you are breaking any rule or you are breaking a use case, you can always validate this against this rule. Maybe what I will do is I'll prepare a separate slide where I will describe each relationship and what it is used for, and that can be your reference guide when you make changes to the code to make sure that you're if you add a new relationship or delete an existing relationship, that you can validate that against those rules. And the other stuff is, you must have seen the change request that I sent yesterday, which I basically found out that those qualified aliases are useless. And I've actually accordingly changed the slide to not have those qualified aliases in the call sense. So you can you may inspect the code and approve it, and then I'll go ask Alan for final LGTM.
Sounds good.
So it is 2:45. So let's brainstorm about a union. So a union operator, I actually haven't fully thought through this, so I may stumble. So a union operator is actually a union construct in SQL is actually two relational operators. It's actually a merge, which is basically get the rows from two different sources. That's basically what merge is. And a aggregate, which is eliminate duplicates. So that's what union does. So union is actually two operators.
Right, depending on, I feel like there's a union, right? There's union and then union all or something.
Yeah, union all. So union all is actually a one-to-one. Union all is an exact merge. It maps to a single relational merge. But a union itself is actually a union followed by a merge followed by an aggregation. So many people don't know this. They tend to write unions where union all could have actually worked equally well. And they don't realize that they make the engine do a lot of additional work just because they don't use the all keyword. A union all is like orders of magnitude cheaper than a union. Because if you do a union all, the engine just returns all the rows it gets without any post-processing. If you just did a union, then it has to actually sort and merge identical rows. And if you're doing a full table scan on two parts and then doing a union, that's hell of expensive. Super expensive query. So the one thing I would recommend is look at all the union constructs that your engineers are using and ask them whether they really want duplicates to be eliminated. And if they say no, you should make them rewrite it to use union all first in the first place. And the reason why, another reason why you should do it is because union all is an opcode that we can very easily support in V3 for the same reason, because we don't have to do any post-processing. Whereas a union is something that we may not be able to support as easily. So like we have described before, we have two strategies, right? We can always try to push it down to the MySQL. If MySQL can handle it, we push it down. So if we get a union and we somehow figure out that it all belongs to the same route, awesome, it goes down. If we get a union and we figure out that they are not the same route, but if it's a union all, then we can still support it, because all we have to do is create a merge opcode, right? The merge opcode is actually very trivial. Instead of J, I will call it M, right? And my job is done. Well, there's a few more lines of code to be written, but that's almost as trivial as that. A join, the only difference, I guess, a merge is actually better than a join, because a merge can run queries in parallel and send the results as they come. Whereas a join has to do a nested loop. A merge just scatters all the individual queries to different parts and just stream the results as they come. It's as simple as that. As a matter of fact, there is already code for it, which is done by the scatter route. So it's basically a special case of a scatter route. A scatter route sends the identical queries to different shards, whereas a union all sends non-identical queries to different key spaces or shards or databases. But what it does with the results is the same thing that scatter would do otherwise. So that makes sense?
Yeah, that makes sense. So it sounds like what I was kind of thinking is that we basically, for merge, would have to create another primitive, but it would be like almost identical to join in terms of the code with some slight differences.
Correct. But the execution is different. In the case of a join, you drive the left, you start with the left and go to your right. Whereas in the case of a merge, you will fire off both queries at the same time.
Right. Yep.
And just merge the results, just like a scatter route would do.
Yep.
So merge is basically a scatter route, but with different route opcodes.
And then we're going to do the same thing where we're actually only supporting union all. So like if we detect a union, then we fail out to like unsupported construct, but we do this for union all.
Correct.
No, I guess it's not that simple.
Union also, you do the pushability analysis, right?
Yeah, that's right. That's right. If we can't push it down, if we can't push it down and it's not an all, then we fail to unsupported.
Then you fail as unsupported.
Okay.
And the common use case for this is if the union is on the same unsharded key space, right? That's a brain dead push down.
Yeah. It's going to be a little funny. It's a bit of a leak of abstraction. We're going to tell the user something about like cross-shard union. You know, in this error message, when we say like unsupported construct, I need to say something more.
I think
we're going to say
all unsupported constructs say so.
Okay.
Yeah. If you look at the entire list of unsupported constructs, it's obvious that many of those are failing only because they are cross-shard. Cross-shard or cross-key space. Yeah, no two ways about it. When you can't do something, you can't do. And this is actually the place where I see Vitess as collaborating with the application. The reason why we return it as unsupported is probably also a reason for you to think about why it is unsupported. It's probably something that's too expensive or too complicated, maybe you should look for ways to achieve the same thing using different methods.
Yeah, I just took a look in unsupported and whatever unsupported cases and saw this. Yeah, unsupported construct, key space, blah blah blah. So cool.
Yeah. So, but if you did this way, if you implemented union all, what's great about it is it interacts with the rest of the opcodes just as a first-class citizen. What does that mean? That means that you could have a union underneath a join. You could have a join underneath a union. It doesn't matter. You don't really care. As long as the operations are meaningfully combinable, then you can actually have an execution tree that combines routes, joins, and unions in any order. And they will all work. So it will not just be for that one special case. I don't know if you can make constructs where there are unions inside joins or joins inside unions. I assume it's possible. But
Yeah,
if that,
I mean,
whether you can build meaningful, if there are meaningful use cases for such queries. But if queries come in, we can handle it by the fact that as long as the relational rules apply and we are able to build these opcodes, then the system will do the right thing for you.
Yep.
Cool. So I will, for Monday, I will try to, I'll see if actually, I have a feeling that you have a better grasp of how things work. So maybe I'll skip the part of building slides for the merge operator.
Just as an FYI, you're still showing us your screen.
Yes, okay. That's the intent. I'm actually going to make the font bigger so you can read it. Where shall we begin? Actually, let me go to the. Let me make the font bigger first. Let me know when you are able to read.
It was actually perfect at the very beginning.
Really?
Yeah, for me anyway.
Yeah, we're not presenting. We're watching it on our laptops. So.
Okay. So this is good now.
It was perfect actually at the very beginning.
Like you want it smaller?
Yeah.
Oh, okay. I'll keep it bigger because I don't know how it will appear on the recording. So.
Oh, that's right. Yeah.
So this looks.
I think that looks reasonable.
Yeah. Okay. So I'm going to go to. Okay. So all this stuff that I've described is under this directory, which is go VT VTGate plan builder, and you can see all the you can see like the various components. Like there is a join tab, which stands for the join table, post processing constructs, select constructs. If you look at the word count, anybody can take a guess as how many lines the entire plan building is?
A few thousand. I don't know.
3,000 lines of code. So this includes selects and updates, inserts, and deletes. So basically, all selects and all DMLs. So it's actually very, very compact code because of the fact that we use a lot of recursion and there's a lot of reuse. So all these features, only 3,000 lines of code. Let's see.
What is the tab again? Is that when two sim tabs have been joined or no?
Symtab is your symbol table.
Right, but what's join tab?
Oh, the join tab is the join table. It is basically a new symbol table, which I didn't cover here, but it's actually a very simplistic table. It's actually it's basically the symbol table that I use at the time of the wire up phase.
Okay, cool.
So during the wire up phase, I do need to keep track of basically the bind variables that I'm creating. I need to keep track of metadata for them, and that we need a symbol table for that, and I call that the join tab.
Makes sense. So that has all the external references that you created.
Yes. Yeah. It basically keeps track of external references and where they are coming from. And if two different sections of a plan request the same table, the same column, then this guy says, oh, by the way, this symbol is already being provided by so and so, and therefore you may not have to go and ask for it all the way to the original query. Find out where in the tree it is available and try to fetch it from there.
Cool.
So that's what it is used for. So so the starting point, the reason what I'm giving you this is to give you a starting point, just so that you can browse, because the next 3 days we are not going to meet. So you can start browsing, and many of the things will actually be obvious. So build is actually the entry point, the main entry point for the plan builder. And then builds an AST and then says build using this. So it's basically, so this is the starting point. As you can see, if it's a union, we say sorry, unexpected. We say it's unsupported construct. And every opcode like join or route has to satisfy this interface, the builder interface. And as you can see, like the first one is give me your sim tab, which means that join needs to know which symbol table it's part of. And when you build the merge opcode, you'll need to make it implement all these functions that this builder has. And if you look at here, there is a join.go, which is the join opcode. And there is the route.go, which is the route opcode. What you would end up doing is building a merge.go, which will be your merge opcode. And if it's a select, which is actually the most complex part of this thing, we save the bind vars away so that we don't accidentally generate a bind variable that is already in use inside the subquery. So that's what that one is for. So if you look at process select, that is basically where everything begins. And process select actually is used recursively when we analyze subqueries. Like for example, here, I see, oh, I detected a subquery, therefore process the select, and then do some additional post-processing. In this particular case, it is the find route. The find route is the most magical function in this entire code base. And the reason is because it is used universally by all constructs to identify the rightmost route rule. So I call find route from when I analyze on clause. I call find route when I analyze the where clause. I call find route when I analyze select expressions, having clause. I think that's about it. So pretty much every important clause in a subquery calls find route. And the advantage of this is that if find route says that there is a target route for this construct, then my job is done. I just push that AST element into the subtree, and then I'm done. So as long as find route succeeds, all I'm doing is pushing down AST elements into the various parts. And if find route succeeds for all of them, my job is done. My route is built, and where we can execute the plan. If find route fails, then we have to decide what to do about it. And as you can see, union operator in subqueries. I believe union operators are not supported in subqueries even within MySQL. So this may actually be something we don't really have to ever solve. But complex joins are definitely supported. So that is something that we have to someday take a look at. So feel free to browse the code. And next Tuesday, 2 p.m. is when we meet next. We can actually drill down into this code. And if you have any questions, you can come prepared, and we can address those also.
Sounds good.
All right.
Sounds great. Thanks.
Have a good weekend.
Thanks, you too.
You too.